Welcome back to Statistical Methods. This is week 12, lecture 1, where I will be continuing to cover correlation and also move on to linear regression, which is a very related statistical process to correlation. So, as far as announcements, please view the updated course calendar to obtain the schedule for the rest of the semester. The course calendar makes it very straightforward. Now let's get into it, and we'll talk a little bit more about R, the correlation coefficient. So, like the sample mean, the correlation coefficient is a descriptive statistic. In this case, one that tells us the degree of interrelatedness between two variables, based on actual data collected from our sample. However, we may also want to conduct inferential tests with R, asking whether our sample R significantly differs from 0. So the logic here is similar to that of testing a hypothesis about a mean. So imagine a population of people measured on two equal interval variables for which there is some true population correlation coefficient, which is called rho at the population level. And we repeatedly sample 10 people from this population and calculate a correlation coefficient R based on each sample. We can then plot all of these individual R's to get a sampling distribution of correlation coefficients based on our samples of n equals 10 participants. Now, if the null is true, the distribution should be centered around R equals 0, that is, no relationship between the variables. So following the same steps we've used previously, you might assume that the next step in this process would be to calculate a statistic that looks something like this. Your sample statistic R minus the null distribution of R's, the mean of the null distribution of R's, divided by the standard deviation of the null distribution of R's. So we'll need to figure out how to get the standard deviation of this sampling distribution now. But it turns out there's a simpler way than this. Instead, we can transform our sample R to get a statistic that is distributed according to a t-distribution, with a degrees of freedom of n, big N, so the total sample size, minus 2. So note here that the presence of R in the numerator means that the larger the R, the larger the t statistic, either positive or negative. In R equals 0 will lead to a t of 0. So this is your formula. And after converting your R to a t-score, you will proceed as if you were conducting any other t-test, specifying tailoredness, significance level, and degrees of freedom to get your cutoff value, then testing whether your t-score is more extreme than this cutoff value. Or you could just find the p-value of your sample t-score and then compare that to your significance level. So we learned how to do this in Jamovi last time, so I won't talk about how to do this by hand. In social sciences, we will generally use a statistical program to do this, and whenever you run a correlation, it will tell you whether or not it's significant based on this test here. So common practice in psychology and all social sciences is to interpret the practical magnitude of R according to the following cutoffs, based on Cohen 1988. An R of roughly 0.1 is weak, an R of roughly 0.3 is moderate, and an R of roughly 0.5 is strong. And of course, anything above that is strong as well. That's also true for negative R's. So while these work fairly well as a general rule of thumb for interpreting R in the social sciences, context must always be taken into consideration when determining what size of effect should be considered to be of practical significance. For example, a correlation between taking aspirin daily and heart attacks of R equals negative 0.034 is a tiny correlation, but in practice this meant that amongst a sample of 20,000 people tested, 72 more heart attacks occurred in the group that did not take aspirin, a difference that we should consider meaningful, even if it's not statistically significant. So another issue with correlation comes down to causality and the third variable problem. So just because two variables are correlated, this does not mean that we can say one variable has causal influence on the other. As an example, imagine we find a fairly strong correlation between earned income and self-reported levels of happiness of R equals 0.6. There are several possibilities here, though. One is that more money causes greater happiness. Another is that people's happiness causes them to make more money. Or 3, some third variable and maybe even a fourth variable and fifth variable, is the true cause of both of these. So maybe it's extroversion. Maybe extroversion causes people to be both happy and to earn more money. Maybe it's ambitiousness, or how much money a person's parents have. So here is a diagram of all of these possibilities. Income might cause happiness, happiness might cause income, or some third variable like extroversion, ambitiousness, or the amount of money somebody's parents have could cause both income and happiness. But there's really no true causal relationship between income and happiness. So based on our income happiness correlation alone, there's no way to know which of these is actually the case. It's likely that some combination of things are going on. So this will be the case whenever the independent variable is merely measured, that is, some pre-existing attribute like religiosity, gender, or age, as opposed to manipulated. So variables which have nothing to do with each other in the causal sense may nonetheless be correlated. You could click on this link here for a demonstration of spurious correlations. Now, to isolate cause and effect, researchers must conduct true experiments, which attempt to isolate just one possible cause for a given behavior by manipulating, as opposed to simply measuring, the independent variable across groups, holding all other variables constant. So imagine a juror decision-making experiment in which mock jurors deliberate either individually or in groups. So if participants are randomly assigned to condition, that is being alone versus in a group for deliberation, and we find some significant difference between them, that means that there is something about group decision-making context that's directly influencing scores. Why? Because this manipulation should be the only way our groups differ. Thus, the only thing outside of random chance factors that would cause these scores to differ. Another important aspect of experiments is that they have temporal precedence. You manipulate your independent variable before the dependent variable is measured. That means that the dependent variable can't be causing the independent variable. So unfortunately, many variables of interest to social scientists can't be experimentally manipulated, like most demographic variables. Researchers in these contexts have no choice but to rely on correlational methods. However, there are ways to make a stronger case for a measured variable being a cause of some dependent variable, primarily by controlling for other variables that might explain variance in our dependent variable. Essentially, this allows us to ask, what is the effect of x on y when variable z is held constant? So what is the influence of socioeconomic status on income after controlling for differences in IQ? So this makes a stronger case for socioeconomic status being causal in this context. And this is possible in the context of linear regression, which we'll learn next. So take a look at these headlines here. Too much sitting may raise a women's cancer risk. Chocolate protects against heart attack. 3 or more servings of chocolate a week reduces the risk of heart attack, finds study. So be wary of this fact when reading articles and reporting correlational research. Authors of correlational studies will often slide into using causal language. So talking about one variable influencing or affecting levels of the other, despite the fact that they have no evidence to support these causal claims. So always think about what other variables, besides the ones being focused on by researchers or journalists, might actually be responsible for the patterns witnessed in the data. Simply put, if you don't experimentally manipulate your independent variable, you can't say it caused anything, or raised the risk of something, or protects against something. Another issue in correlation is restriction of range. Sometimes studying only a subset of a larger population, so a restricted range of the possible values of a variable, will lead us to miscorrelations that actually exist in the larger population. Or the opposite could be true. You might assume there is a correlation when there actually isn't one, by only looking at a subset of the possible range of values. So what would you conclude about this relationship between geography knowledge and grade level based on each of these two graphs below. So the first one here, it doesn't really look like there's any relationship because we're only looking at a restricted range of grade levels. This doesn't really look like it would follow the pattern of a straight line. But when we look at the graph showing all of the possible grade levels, we do see that there is a linear trend. So when you truncate this graph and only look at grades 1 through 3, geography level and grade level don't really track together. But when you look at them across grades 1 through 12, they track positively and linearly. Another issue in correlation is the influence of outliers. Take a look at the score here. So outliers, or extreme scores, can also exert a disproportionate influence on correlation coefficients, especially when dealing with smaller samples. So here is a graph of the relationship between hours slept last night and happy mood, and we have an outlier up here. So when we include this outlier in our calculation of R, we get an R of negative 0.11. But when we exclude this outlier, we get an R of positive 0.85. So not only did the inclusion of the outlier make this correlation coefficient weak, it made it negative, when in actuality the relationship seems like a strong positive relationship. So let's move on to linear regression. Correlation and regression are very overlapping approaches that give us similar kinds of information about relationships between equal interval variables. The main distinctions, though, are that linear regression approaches these relationships from the conceptual framework of prediction of variable y from variable x. And as we'll see, linear regression generalizes beyond bivariate or two-variable relationships and allows us to test a broader variety of research questions than correlation does. So regression focuses on the linear prediction rule, or regression line, the equation for the straight line that best fits the observed data. And the basic logic is this. Knowing a person's score on variable x, let's say it's right here, and knowing the equation for this line of best fit, the regression line, I can predict this participant's score on variable y. So the scatter plot to the right displays the relationship between advertising dollars spent and sales in units of $1,000. Using the line that best fits these data, we can make predictions about sales on the y-axis based on the amount of money a company spends on advertising on the x-axis. So if a company spends roughly $6,000 in advertising, we could assume that this company will sell roughly $110,000 or $111,000 in sales. If they spend $6,500 on advertising, they'll sell between 16 and 20. $116 and $120,000 in sales. So to conduct a linear regression, we'll need to answer the following questions. How do we define the line that best fits the observed trend in the data? How can we determine the characteristics, so that's the slope and y-intercept of this line based on the observed data? And how do we use these characteristics to make predictions from x to y? So before we do so, it's useful to answer the question, when do researchers use linear regression and why? So although we'll first see how we can make predictions from x to y about individuals using the linear prediction rule, researchers don't usually care about making predictions for one person. Remember that almost always psychologists and social scientists' goal is to make inferences about the general population of interest. Knowing M is more useful than knowing X in achieving this goal. Instead, researchers usually want to know how well they can make predictions from x to y. In other words, how good of a predictor is x for y in terms of the strength and direction of the relationship. But wait, isn't that what we just achieved with a correlation coefficient? Yes. So what is the point of linear regression? Well, there's only one x predictor variable. When there is only one x predictor, correlation and regression gets us the same basic information, with the only significant addition being that knowing about the shape of the best fitting line. Usually, however, researchers are interested in examining multiple predictor variables at once to determine their relative predictive power. So how well do IQ, parental income, SAT scores, and high school GPA predict college GPA? In this kind of analysis, we'll be able to determine to what degree each of these predictors uniquely predicts college GPA. By uniquely, I mean above and beyond the other predictor variables in the model. So we will still mostly focus on the one predictor variable and one outcome variable situation in this class, just to get the basics of linear regression down, but know that this does exist where you can use multiple predictors in one model. So imagine that you wanted to predict someone's undergraduate GPA based on their SAT score. How would you go about making this prediction? Well, one way is to assume that GPA will look like the average undergraduate student and predict that their GPA will be the same as the mean GPA of all undergrads. It's simple, but ignores the useful information that we have, SAT scores. Second way would be to set up a series of rules for making predictions based on SAT scores from what we know about past students and apply this. So students with SAT scores between 300 and 400 typically end up with a mean GPA of 2.7. Students with SAT scores between 600 and 700 typically end up with a GPA of 3.6, and etc. It's more accurate than just using GPA, but it's overly tedious and complicated, and would rely on a number of arbitrary decisions. Same point I made earlier about the difference between categorical independent variable, base, ANOVA, and correlation. So the best way is to use the straight line that best describes the data to make predictions by applying a general linear prediction rule requiring two steps: multiplying the person's score on the predictor variable by a regression coefficient, denoted as B, and adding a constant, denoted as A. So in this equation, y hat is the predicted variable on the outcome, is the predicted value on the outcome variable for a given value on the predictor variable x. Thus, assuming we can figure out the coefficient b and a constant for the line that describes our data, we can make predictions about the scores on the outcome variable by plugging in these values, along with the x value, the predictor variable score. So the linear prediction rule for predicting a person's undergrad GPA based on their SAT score might look something like this. Y equals a plus bx equals 0.3 plus 0.004 times x. Remember, x here will be the SAT score. And this right here is the slope of the line. And this here is the y-intercept. So using this, we could predict GPAs based on a variety of SAT scores. So let's say somebody scores a 700 on the SAT, and we multiply that by the slope of 0.004, and then add 0.3, and we get 3.1. So that's how we can predict somebody's GPA based on their SAT score using this model here. Somebody scores a 300 times 0.004 plus 0.3 equals 1.5, and so on. So you may recognize this formula. It is the same as that for a straight line, though sometimes using different letters like y equals mx plus b. Here it's y equals a plus bx. This should make sense since we are making predictions based on the line that best fits the data. So the linear prediction rule, or the regression line, is the line that best fits the points in the scatter plot. So remember that our ability to make predictions using this line will ultimately come down to how close to a straight line the relationship between x and y is. So that is the strength of this relationship. assuming it is indeed a linear relationship. What happens when there appears to be no relationship between our variables of interest? So with a near zero correlation, our best fitting line will simply approximate a horizontal line near the mean of y. Thus, regardless of a person's score on x, our best prediction will be the mean of y for any person. So in these situations, knowing x doesn't really help us predict y because the variables are unrelated to one another. The regression line has two central characteristics of interest to us, which correspond to the regression coefficient, or b, and the constant, a, we already discussed. The first is slope. In other words, how steep the angle of the line is equivalent to the regression coefficient, b. So b is the slope. This is the amount that the line moves up for every unit it moves across, or rise over run. So in our SAT example, we had a regression coefficient of 0.004, meaning that for every additional SAT point, there was a 0.004 increase in GPA. Or in more useful terms, for every additional 100 points on the SAT, we could expect a 0.4 increase in GPA. So b equals the regression coefficient, or the slope, or how steep the line is, or how much the line moves up for each unit across, rise over run. Now, what is the slope of this regression line? So if we look here, remember the formula for slope is rise divided by run. So 6 divided by 9 is 0.66. So that is what b is equal to. Now the intercept is the other point that we need to know for regression. It's the point at which the regression line crosses or intercepts the y-axis. This is the y-intercept in linear mathematics. And this is equivalent to the regression constant, a. So a is the y-intercept. It can also be thought of as the predicted score on y for someone who scores a 0 on the predictor variable x. So in our SAT example, for someone who scores a 0 on the SAT, this person would be expected to have an undergrad GPA of 0.3, the A for the linear prediction rule. So that's a good way to find the intercept. Plug in 0 to your formula. So A is the regression constant, the intercept, the point on the y-axis at which the regression line crosses. So what is the intercept of this regression line? Looks like it's roughly 0.25. So next class we'll learn how to calculate the regression coefficient and constant given a set of scores, or pairs of measurements taken from the same individuals. We'll then discuss extensions of regression beyond the bivariate context. That's all I have. Have a good rest of your day. Thank you.